Good morning. This is lesson one, which is why unreliable software is a big deal. Software is doubling in size about every 4 years. The excessive cost of failures and defect fixing is another reason. It's a leading cause of canceled programs. Software failures have caused fatalities. A single failure can cost billions now. Software nearly started a nuclear war. Software failures can affect every system at the same time. They can cascade quickly. There's an old saying that it will never happen until it does, and that is very true for software failures. We're also going to discuss kind of the bad things that can happen when software fails. And we're going to summarize this lesson with the fact that the current mode of operation is not working with regards to software development. Okay, let's talk about the software statistics for the size of software doubling. You might be saying, well, what difference does that make if the software size is doubling? Anytime something doubles in size, the proportional number of defects will also increase with it. It's simple math. If you have more software, you have more that can go wrong. A big piece of equipment has more that can go wrong than a little tiny piece. So now the problem is, while the size of software is doubling every 4 years or so, the ability to develop and test the software and make sure it's reliable, that's not increasing every 4 years. We have data to show that the development practices are holding steady. They're not improving over time. And in fact, and there's some data to show that things could possibly even be regressing. So because of this, software is now the dominant component in mission critical systems today, yet it continues to kind of be the leftover child that doesn't get a lot of attention. Okay, the cost of unreliable software is excessive and increasing every year. This is some data that we have on cost starting from 2018 to 2022. We retrieve this data from a reputable third-party source that does nothing but track cost. So according to them, 35% of projects are fully successful with respect to time and budget. That means the remainder are not. 19% of software projects failed, meaning completely didn't get off the ground because of unreliable software. Now, when you look at this table, the United States accounts for 31% of all software development, and this table shows the US statistics. So if you want to know what it is worldwide, just multiply it by about 2, and that'll tell you what it is worldwide. Okay, so if we look there, the cost of software failures, this includes all costs, tangible, intangible, loss of business, loss of revenue, etc. You can see there's a 42% increase over between 2018 and 22. And the numbers now are almost 2 trillion for cost of software failures in that given year. Just so we're clear, this is in that given year, not cumulative. The cost of technical debt for that year has increased about 16% since 2018. It's now up to about 1.5 trillion. The cost of fixing defects, this source did not, they weren't tracking this in 2018. They started in 2020. We could see a 21% increase just between 2020 and 2022, with the cost of fixing defects about 607 billion. And then we look at the cost of unsuccessful projects for that year. We see an increase of 46%. So the cost of unsuccessful programs is even much larger than the cost of fixing defects. So I do want to point out technical debt is the backlog of unfixed defects. So that's what that second column means there. Okay, let's look at the canceled and distressed programs. These are just a few of them. Uh, the F-35 was one of the largest software systems. It did not get canceled, but it came close on several occasions. There have been times of poor reliability. Initially, that was definitely the case, and there's been a few times since it was first developed. The Future Combat System was canceled. It was had poor reliability. It was late, and it was underscoped and over budgeted. Healthcare.gov was not canceled. It did have very poor reliability initially. While it wasn't canceled, it was basically changed to be outsourced as opposed to government run. The Denver Airport luggage handling automation system was one of the worst examples of cancellations. The software itself cost about $500 million, but because the failed luggage handling automation, the city of Denver did not become a hub, which had an additional cost of loss of potential jobs. So these are just a few examples of canceled and distressed programs. Okay, a few software failures have led to, these are just a few that have led to fatalities. There are others other than what's on this list. Most of you are probably familiar with the 737 MAX. There were 346 fatalities over 2 flights. The Therac 25 over radiation had at least 5 fatalities, maybe 28. With over radiation, it's difficult to determine. Some people may have died from the radiation, some may have died from they were going to die anyway, so that's why there's a range there. The Panama City over radiation was 28 people. They do know how many people were over radiated. The Scud missile attack with the Patriot missile system also took 28 lives, and the AFAD's friendly fire was 2 fatalities in that case. Okay, in addition to safety, there's also the fact that some of the software failures now are what I call super catastrophic in cost. That means they're well over $1 billion. So the first one is the CrowdStrike that just happened this year. Right now the cost is at $5.4 billion. It's expected to increase with the pending lawsuits. And the 737 MAX for 2 failures, 2 flights, was in excess of $18.7 billion. So here we have very high cost of just a single failure. Okay, 1983, a software failure nearly caused a nuclear war. The Soviets had designed an early warning radar system to detect incoming threats like missiles. In 1983, that system, it was called OCO, had a software malfunction. Some alarms rang out indicating an incoming missile. Fortunately for everyone, Mr. Petrov was an officer on duty. He was familiar with the software. He was aware of the fact that it had some problems with it. So he rebooted the system. It did not clear the alarms. So he waited for evidence for a missile attack that never came. Just to be clear, the reason why we talk about this is that the protocol for him was to initiate a counterstrike. If he had followed orders, there would have been a nuclear war. Okay, another issue that we have with software that we don't see so much with hardware is that the same defect can cause failures in multiple systems at the same time. So the example here is the F-22 fly over the international date line from Hawaii to Japan event. The software was missing logic for what to do when the aircraft crosses the international date line. Some people call this a coding failure. No, it wasn't. It was a design and specification failure. No one thought about the international date line. They never wrote the code to handle that. So just to provide some background, at the international date line, time changes and so does longitude. It resets. Those 2 things can affect software. It can affect navigation, and that's exactly what happened. The navigation was lost despite repeated reboots by the pilots. Fortunately for them, it was daylight and there were ships below them. So they're in the middle of the Pacific Ocean. They don't have any guidance. There's no landmass for them to be looking at for guidance. So fortunately for them, they were able to turn around. And some people say, okay, what was the big deal? Well, the big deal is we could have lost all those aircraft and those pilots very easily. And also the mission was lost. The mission included things other than the aircraft. It included the ships as well. All of those people, all of their time, the gas, all of the ships, all of it was lost. So this is not a small failure here. So just to recap, with software, you can have every system fail at exactly the same time. Okay, another problem we have is that software failures can cascade, and hardware-centric risk matrices don't work for software, unfortunately. So there's a variety of reasons why our hardware-centric risk matrices don't work. First, they don't think about the cascading cost. So the cost of recalls, loss of business, refunds, tech support, warranty, and outages. They tend to look at the cost of losing the hardware, or the immediate cost, which is often the smallest cost. They also don't think about likelihood, as we discussed on the previous page. The software failures are not caused by random events, they're caused by defects. And those defects are in every installed site. And so we can't look at software failures as being random, because they aren't. Even though they may seem like they are, they're not caused by a random root cause. So here is a notional example for the NATS failure that happened in August of 2023. The NATS is the National Air Traffic Services software. It had a 1 in 15 million flight defect that caused the flight plan to not work. And the effect ended up being 250,000 flights had to be rescheduled at the cost of $127 million. The airlines are not happy about this failure, and they believe that they should not have to pay for that cost. So one thing I do want to point out is this is a notional example of the NATS failure. Now, obviously, they didn't know about this until after it happened, so this is notional. But if you look at it from a hardware-centric point of view, they would have looked at just one flight, the cost of rebooking passengers from one flight, which is not in the super catastrophic range or catastrophic. It's critical. You know, you have a few hundred people that have to be rebooked. You lose revenue on those. No loss of hardware. Likelihood, they know it was 1 in 15 million because that's how many flights had transpired prior to this event happening. So when you look at remote and critical, you get an assessed risk level low. In reality, the actual cost is catastrophic. It's well over 10 million, because this didn't affect just one flight. It affected all of them during a 1 or 2 day time frame. 250,000 flights at 127 million, which is well into catastrophic. Now, when you consider the fact, yes, it's 1 in 15 million flights, but there's 35 million flights a year. So when you look at it that way, instead of looking at one flight, look at the sum of the flights. Now we have a likely event, and the assessed risk level is therefore high. This is something that our company is trying to change in the international standards, is to change the risk assessments to actually reflect the true cost and the true likelihood. Okay, there's a common saying, it will never happen, ... and then someday it does. And with software, this is a repeating story over the last 60 years. The Ariane 5 explosion is a classic example of this. There was a potential floating point error in the code. The software engineers knew about it. They knew that potential existed, but they assumed it would never cause an overflow in the velocity calculation. The velocity calculation, by the way, on a spacecraft is probably one of the most mission critical things you can have. So it's not an area that you should really be taking chances in, but they did. So the assumption that this failure would never happen never had any scientific justification. Number one, the defect existed and they knew it. So therefore you can't say it's impossible. Two, there was no control for that overflow. In order to say something is impossible, you have to have multiple controls. They had none. Their only basis for this claim is that they didn't see an overflow on Ariane 4 and it had the same code. The problem with that logic is that Ariane 4 had a different payload and launch trajectory, which affects velocity calculations. So the effect was, because of the different payload and launch trajectory combined with this defect, at liftoff, at first everything was working fine, then the overflow occurred, the stack overflowed, the processor encountered an operand error because there was no control for the overflow, and it populated the horizontal bias variable with a diagnostic value, which caused the software to reboot, and the spacecraft exploded. So I do want to point out there was a missed opportunity here. The people say, oh, we can't test for everything, blah, blah, blah. This would have been found with a single true trajectory in simulation mode. Just a single simulation with the actual launch trajectory would have uncovered this failure. This did not require years and years and years of regression testing. One simulation with a true trajectory would have identified it. Okay, big things happen when software engineers don't pay attention to requirements. The very first recorded software failure in modern history was on the Mariner 1 launch in 1962. Basically, this was also in velocity calculations. It's a kind of an odd coincidence here, but the formula that was in the specification required that the velocity calculations be average, so it had an overbar on it. All engineers know what an overbar is. It means average. This software engineer, who did understand engineering, missed that overbar, and instead of coding the average velocities, they coded the raw velocities. So what happened is, on liftoff, the raw velocities appeared as if they were big variations when really the spacecraft was on course. So the software tried to make faulty corrections to the course, which was not problematic, and those faulty corrections actually caused it to go off course. The rocket was destroyed a few minutes after liftoff. In today's dollars, it'd be $193 million today. Now, back then in 1962, there was no software engineering practices, so we can't be overly critical of this. But in today's world, a 30-minute code review to compare the code requirements would have identified the defect. This didn't happen then because, honestly, back then, nobody knew that software could actually fail. Okay. All right, and bad things can happen when engineering skips on end-to-end tasks. An end-to-end task is exactly what it sounds like. You start at the beginning and you simulate all the way to the end. The Cryosat-1 is one example of this. The Mars Climate Orbiter is actually another example as well. You can research that one. But in this particular case, there's a thing called a MECO, a main engine cutoff. It's on nearly every spacecraft. It cuts off the fuel once the spacecraft gets beyond the first stage of launch. That code was missing. So on launch date, everything was successful right up until the second stage. The engine didn't cut off, and it continued to operate until the fuel was consumed, the satellite was lost. This is $2005. It was $186 million then. It would obviously be more now. Now, the missed opportunity here in 2005, people did understand software engineering and testing. There was a very clear missed opportunity here. One, end-to-end simulation, meaning crossing over, a simulation that crosses over the phases would have identified this defect. So the cost of one simulation is minimal compared to this failure. Again, this did not take years and years and years of testing or millions of dollars worth of test effort. One simulation is what we're talking about here would have identified this failure. Okay, and bad things also happen when people assume the software specifications themselves are good. I know I'm showing a lot of space-related examples here, but part of it is that the space-related examples are very well documented. Okay, so this came from the DART spacecraft issue, the demonstration of autonomous rendezvous technology. And there are two DART spacecrafts. This one is not the most recent. This one's a couple of decades old. Now, there was a requirement that the GPS receiver to the software-based estimates had to have an accuracy of plus or minus 2 meters per second. The problem with that specification was the number 2. It should have actually been the number 1. The specification itself, we call this a magic number. The magic number was wrong. And so what happened is, because that number was too big, the bounds were too big, the estimates diverged from the measurements and triggered a reset, kept resetting. It missed its critical waypoint to switch over to nav. The nav system could not accurately determine its velocity or position. It's basically lost in space. Whenever you've been lost somewhere, you waste fuel trying to find where you're supposed to go, and that's exactly what happened here. So about 11 hours into the 24-hour mission, it collided with the satellite, the Mobilecom, and it ran out of gas, and that was the end of that. So the process failure here is failure to require all scientists who write numerical values into a specification to actually prove that that number is correct via modeling and simulation. Okay, that was the process failure. Okay, bad things also happen when no one thinks about how to handle faults. In any engineering system, it is guaranteed something's going to go wrong. In the hardware, the software, the weather, whatever, something's going to happen. And the first example of this is Apollo 11 lunar landing. Neil Armstrong was forced to manually land because of repeated restarts. Now, fortunately, he was able to manually land. If he hadn't been, the whole landing would have been canceled. So while this didn't have direct dollar cost, it did cost a lot of angst that the landing could be canceled. Okay, so each time the software detected 2 particular alarm codes, it rebooted, it restarted the important tasks like steering and descent, but did not start the erroneously scheduled rendezvous radar jobs. So basically, the source of this was priority inversion, but no fault handling on that. The software kept rebooting when what it should have done was something else. It should have appropriately handled this instead of continually rebooting whenever something is wrong. The rebooting thing just made things worse. Okay. I also want to point out we went through a lot of failures, and I did show a lot of things from the space and aviation industry and medical devices, but I do want to point out virtually every industry has been affected by unreliable software. You can see here some of the many events. You feel free to do an online search on these. They've affected medical, defense, space, aerospace, finance and banking, transportation, energy, entertainment, the semiconductor industry, major appliances, really just about anything with software has had something happen. It's not just space and aerospace. Okay, so let's wrap up our lesson 1. The software development processes aren't working. If they were, the statistics that I've shown you here would simply not be the way they are. With software doubling in size every 4 years, honestly, things are going to get worse, not better. Um, if software reliability isn't addressed, you can count on things like excessive warranty costs, excessive waste on defect fixing that erodes profitability. You might encounter one very serious failure. You also might encounter several failures that make the system unusable for your customers and your users. You might encounter a cascading failure that has cascading costs. And there also might be generally unstable software that leads to a program cancellation. A lot of the programs that have been canceled weren't really due to one failure, they were due to many, many problems. So a collection of unstable software failures. All right, we look forward to seeing you in the next module, lesson 2.